A-Level Mechanics, Momentum and Impulse, an Introduction. A couple of new ideas we can add to mechanics are momentum and impulse. Now we already know Newton's second law, F equals ma. And we can multiply both sides of that equation with the letter t. So that gives us Ft equals mat. Now if the acceleration is constant, we've also got v equals u plus at. In other words, at is equal to v minus u. Now if we substitute at in equation 2 into equation 1, we get Ft equals m into v minus u. And if we expand the brackets, that gives us Ft equals mv minus mu. Now we can get the idea of momentum from this. We say the quantity mv is known as the momentum. So momentum is equal to mass times velocity. Now to get a feel for what momentum is, if you think of an object that's moving, its momentum is a measure of how difficult it is to stop. So for example, if you've got a light object that's travelling very fast, like let's say a bullet, it's very difficult to stop a bullet. It'll penetrate a long way. On the other hand, if you have something that's very big and moving quite slowly, it's also got a lot of momentum. If you think of a lorry moving at even walking speed, if you were standing in the way and trying to stop it, it would be quite difficult. So something that's heavy or something that's moving fast will have a lot of momentum. Something that's light and moving reasonably slowly, such as a table tennis ball, would be very easy to stop. So it would have very little momentum. Now the other quantity in the above equation is Ft. This introduces the idea of impulse. If the force is constant, the quantity Ft is called an impulse. So the impulse is the force times the time. Now if the force is not constant, we can still have the idea of an impulse, but it's a bit harder to define. If we drew a graph, force against time, then the area under the graph would be force times time, which is the impulse. So the impulse is the area under the graph. So if the force is not constant and we draw the graph of force against time, the impulse is still the area under the graph, so the impulse is the integral of f dt. Now, Ft equals mv minus mu tells us that the impulse on an object is equal to the change in momentum of the object. The units of impulse are Newton seconds. Now even if the force is not constant, it's still true that the impulse is equal to the change in momentum. Often a very large force is applied for a very short time, such as when a bat strikes a ball or two billiard balls collide. In these cases, it's very difficult to measure the force or the time the objects are in contact. This makes it very difficult to do any calculations that involve force or time in these situations. However, the change in momentum will be easy to calculate, so we tend to concentrate on the impulse. Such an impact is called an instantaneous impulse. Let's look at an example. Example 1. A ball of mass 0.6 kilograms strikes a wall with a velocity of 12 meters per second perpendicularly to the wall and bounces back with a velocity of 8 meters per second. Calculate the impulse on the ball. Well, to solve this, if we draw two diagrams to show the situation before and after the collision, we have u is equal to 12 meters per second and v is equal to minus 8 meters per second. So the impulse, which is equal to mv minus mu, is equal to 0.6 times minus 8 minus 0.6 times 12, which works out to be minus 12. So we have an impulse of 12 Newton seconds away from the wall. Example 2. A solar sail is driven by the force created when light strikes it. This solar sail generates 0.00085 newtons and pulls a combined load of 1.8 kilograms. It's travelling away from the Sun with a speed of 185 meters per second. In Part A, we're asked to calculate the impulse on it over a period of 10 hours. Well, to solve this, we have the force acting on the panel is 0.00085 newtons. So the impulse is the force times the time. The force acting on the panel is 0.00085 newtons. Now the time is 10 hours, so that's 10 times 60 times 60 if we're converting it into seconds. And if we multiply those together, we get 30.6 newton seconds. So the impulse is 30.6 newton seconds. In Part B, we're asked to find how fast will it be travelling after 10 hours if we ignore the gravity of the Sun. Well, we've calculated the impulse is 30.6, so that means the change in momentum is 30.6. Now the change in momentum is mv minus mu, and that's equal to the impulse 30.6. So 1.8v minus 1.8 times 185 is equal to the impulse 30.6. So 1.8v is equal to 30.6 plus 1.8 times 185. And that works out to be 363.6. So if we divide both sides by 1.8, we get the velocity is 202 meters per second. So the final velocity is 202 meters per second. Now in example 3, we're asked to calculate the impulse needed to accelerate a 1.2 ton car from 20 kilometers per hour to 50 kilometers per hour, if we're ignoring friction and air resistance. Now the first thing we have to do is convert the speeds from kilometers per hour to meters per second. Now, there are 1,000 meters in a kilometer, so we have to multiply by 1,000, and there are 60 times 60 seconds in an hour, so we have to divide by 60 times 60. So the initial speed u is 20 kilometers per hour. We multiply by 1,000 and divide by 60 times 60, and that works out to be 5 5/9 meters per second. The final velocity v is 50 times 1,000 over 60 times 60, and that works out to be 13 8/9 meters per second. Now the impulse is the change in momentum. So the impulse is the final momentum minus the initial momentum. So the impulse is 1,200 times 13 8/9 minus 1,200 times 5 5/9. And that works out to be 10,000. And so the impulse is 10,000 newton seconds. Conservation of momentum. If two bodies collide, each body will have a contact force acting on it while they are together. These forces will be equal and opposite. That's Newton's third law, and will last for exactly the same amount of time. So they will have equal and opposite impulses acting on them. This means that the momentum lost by one will equal the momentum gained by the other. Their total momentum will remain constant. If we have two bodies with masses m1 and m2 and velocities u1 and u2, which then collided, and their new velocities were v1 and v2, then the total momentum would remain the same. m1u1 plus m2u2 would equal m1v1 plus m2v2. Let's have a look at an example. Example 4. In the diagram we see a wooden block of mass 0.4 kilograms which rests on top of a vertical pole 7.056 meters long. The pole stands on horizontal ground. A bullet of mass 200 grams is fired horizontally with a velocity of 800 meters per second and embeds itself in the wooden block. In Part A, we're asked to find the speed of the block and bullet as they leave the pole. We can solve this using conservation of momentum. Now we have m1u1 plus m2u2 equals m1v1 plus m2v2. So let's suppose the bullet and the block leave the pole together with a speed of v. Now the bullet weighs 20 grams, and in kilograms that's 0.02, and the speed of the bullet is 800 meters per second. So the momentum m1u1 is equal to 0.020 times 800. The block is stationary initially, and so its momentum is 0. After the bullet embeds itself in the wood, the block will have a mass of 0.42, so the final momentum will be 0.42 times v. Now that simplifies to 0.42 v is equal to 16, and if we divide both sides by 0.42, we get v is 38.095. So rounding off, we have the velocity of the bullet and the block together is 38.1 meters per second. Now in the second part, we're asked to find the distance back they travel before hitting the ground. Well, the first thing we need to do is work out how long it'll take before they do hit the ground. Now they have no vertical velocity, so using s equals ut plus a half at squared, the initial vertical velocity u is 0, a is 9.8, s is the distance from the top to the bottom of the pole, so that's 7.056, and we're trying to work out t. So 7.056 equals 0 plus a half times 9.8 t squared, and we can simplify that as t squared is 7.056 divided by a half of 9.8, which is 4.9. So t squared works out to be 1.44, which means if we take the square root of each side, t is 1.2, and so it takes 1.2 seconds before it hits the ground. Now we know the combined block has a velocity of 38.095 meters per second, and so the distance travelled is 38.095 times 1.2, which is 45.71. And so the distance it'll travel before it hits the ground is 45.7 meters. Note, an impulse is a vector. We can see that because an impulse is a change in momentum, and momentum is force times time. Now force is a vector, and time is a scalar. A vector times a scalar is a vector, so an impulse is a vector. That means we can have vector equations that are solved using impulses. Let's have a look at an example. Example 5. A body with mass 1.2 kilograms has a velocity of 2I plus 5j meters per second. It has an impulse of 3I minus 9j Newton seconds acting on it. Find its new velocity. Well, to solve this, we can use the impulse is equal to the change in momentum, mv minus mu. Now the impulse is 3I minus 9j. We can let the final velocity be v, so mv is 1.2v, and we know the initial velocity is 2I plus 5j, so minus 1.2 times 2I plus 5j. Now we can rearrange that as 3I minus 9j plus 1.2 times 2I plus 5j is equal to 1.2v. And dividing all the way through by 1.2, we get v equals 3I minus 9j over 1.2 plus 2I plus 5j. And that works out to be v is equal to 2.5i minus 7.5j plus 2i plus 5j. And so our answer works out to be v equals 4.5i minus 2.5j meters per second. Let's look at one more example, example 6. Two balls A and B of the same radius with masses 0.2 kilograms and 0.5 kilograms lie on a smooth level surface with B at rest. A strikes B directly with a speed of 1.2 meters per second and rebounds with a speed of 0.3 meters per second going the other way. In part A, we're asked to find the impact of B on A. Now to solve this, It helps if we draw diagrams of the different stages. In the first diagram we show A moving towards B, then the impact, and then the two bodies separating. So let IA and IB be the impulses on A and B. If we use the equation I equals mv minus mu for the first impact, then we have the mass of A is 0.2, its initial speed is 1.2, and its final speed is minus 0.3. So IA equals 0.2 times minus 0.3 minus 0.2 times 1.2. So that's equal to minus 0.06 minus 0.24, which adds up to minus 0.3 Newton seconds. So the impulse on A is 0.3 Newton seconds back. Now in part B we're asked to find the final speed of B. Now we know IB is equal to minus IA. The impulses are equal but in the opposite direction. So that's equal to 0.3 Newton seconds. So 0.3 equals 0.5 V minus 0. Now we can divide both sides by 0.5. And that works out V is equal to 0.6. So the velocity of B is 0.6 meters per second.